Hi, I'm Brian from Simply Brian Enterprises and welcome to my channel. In today's video, we're going to be looking at the homework solution for TopTechBoy's Raspberry Pi class lesson 5. We're going to take a quick peek at the hardware, the program, and then of course the code. So let's jump in. This week's lesson is centered around building a 5-bit counter out of LEDs. So basically we're going to send a value between 1 and 31 and represent it in binary on 5 LEDs. Paul made a mention of cleanliness of our breadboard, so I'm going to do a little overview here of what I've done. And you can see I've used these short pre-cut jumpers for the grounds for my LEDs to keep the height down and obviously keep the length down. I use my resistors that I trimmed down. You'll see another video that I made about how I sort my resistors and trim the length of the leads to 15 millimeters each. 5 red LEDs, and then when it comes to actual GPIO, you might notice I used the resistor color coding scheme. So these are ordered from bit 0, bit 1, bit 2, bit 3, bit 4, and so I've represented that with the colors of the jumper cables as well. So I've got black, which is 0, brown, which is 1, red, which is 2, orange, which is 3, yellow, which is 4. That way I can keep track of which is which. And I'm plugging them into GPIO pins between 29 and 37. So let's take a quick peek at our program. And I made the mistake of letting it run, so let's clear that out and try again. And so the first thing it's going to do is it's going to go through a quick test sequence, and I wrote the test sequence just to test the GPIO pins, and I thought, well, I'll leave it in. It's kind of neat. So the first thing it's going to ask me is enter an integer between 1 and 31. So I'm going to do 9, and we'll watch it count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then clear, and then it's going to loop around and ask again. And of course, if I press Q here, it will exit the program and do the GPIO cleanup. But what if I put in an invalid number? What if I put in 45? Oh, that's out of range. That's not going to work. What about a -5? You can't represent a negative value in binary. Oh, that's not going to work either. What if I put in E? Nope, that's not valid either. So a lot of that checking that I did in lesson 4, I've moved into lesson 5 as well to do the error checking of the user input. And of course, when I hit Q, it exits the program cleanly and does the GPIO cleanup. So let's take a look at the code and see how I built my program. So of course I did our imports of RPIO and time. Um, First thing I did is I loaded the GPIO pins into an array, and I thought this was a smart idea since I'm numbering the bits from 0 to 4, and since Python is doing everything 0 indexed, I thought it made sense to continue that with an array. I'm also using board numbering. Now I made a slight comment in lesson 4 about BCM versus board numbering. And I want to revisit that a little bit. So my thought when I was building lesson 4 is that BCM is going to be persistent across generations of Raspberry Pi. So if they come out with a new generation and move the pins around, the BCM pins will stay the same even though they might move around on the board. Whereas the board pins, I'm going to have to go into my code and change the numbering. That was my thought anyway. But as I looked into it, I realized that the pin layout on the Raspberry Pi board hasn't changed since Raspberry Pi version 2. Since then, there's been 3 in all its iterations, 4 and 4B, it's been Pi 0, Pi 02, and even though the Raspberry Pi version 5 is on the horizon, that project has been horrendously pushed out because of the chip shortage. So I don't think I have to worry about the pins moving around on the board anytime soon. So for my own sanity, I've decided that from now on I'm going to use board numbering as opposed to BCM numbering. It is personal preference, and that's the preference I've chosen. So now that I've set my mode for board, I'm going to loop through the array and just do my gpio.setup. And for some reason, once in a while, when I run through the setup of each pin, it'll actually set it to high. So I have it going through, and every time it sets up a pin, writes it out as false to turn off the LED. Then what I'm doing is I'm going to do my little startup sequence that you saw. So I'm doing a 1 second sleep there, and then I'm going to loop through the entire set of GPIO pins, set it true, sleep for 100 milliseconds, set it false, sleep for 100 milliseconds, and then obviously loop around and do the next one. And then finally turn them all on, and then sleep for 500 milliseconds and turn them all off. So that's just a little kind of a test program I ran first just to make sure everything is wired up and that all of the LEDs are working. So now let's get into the actual code. And just like we saw in lesson 4, it's going to loop indefinitely until you press Q to quit. So we have everything in a while loop of true. And the first thing I'm going to do is clear the output value. I'm sorry, the output value is the um, integer that we're going to use to represent the binary number, and actually outval becomes input here. That's kind of a misnomer, but anyway, we're setting the value that the user enters, we'll say, as 0, and then I'm going through and clearing out again the state of the LEDs to make sure they're all set to false before we begin. Then what I'm doing is I'm doing my while loop to take input from the user and validate the input. So I'm taking it as string, validating to see if there's a queue. If there's a queue, we're going to do a GPIO cleanup and exit the program. Then we're going to see, is it an integer value? If it's not, we're going to error out. We're going to set outval to 0, which is going to loop us back through the while loop and try again. Then we're going to do a verification that it is greater than 0 and less than 32. So we know it's an integer. It's going to be greater than 0 or less than 32. If it's outside of that value, we're going to say nope, try again, and set our outval to 0, go back through the loop and keep asking until we get either a queue to quit or a valid integer. Once we get down here, we know that we have a valid integer between 1 and 31. We're going to do a 1 second sleep. Again, this is just so I can turn my head and look at the board, so I don't miss that first blink as I'm testing. And now I'm going to get to actually taking a decimal and converting it to binary. So the first thing I'm going to do is I'm going to loop through the entire range from 1 to whatever our user entered. So if it's 4, this will loop from 1 to 5, because you see I did the +1 there, because normally if I did outval, it would go 1, 2, 3. Well, I want it to go 1, 2, 3, 4, so I'm doing a +1. So this is actually, if my out value is 4, I'm going to loop to from 1 to 5. And then I'm going to start doing some math to set my bits. So the first thing I'm going to do is I'm going to divide by 16 and do an integer. Now, in this case, that value is either going to be a 1 or a 0. If it's greater than or equal to 16, my output is going to be 1. If it's less than 16, it's going to be 0. So I look at this and say, okay, bit 4, which is my highest bit on the board, I'm going to say that's a 1 because it's 16 or greater. And then what I'm going to do is, if that's 1, I'm going to decrement the value by 16. So if you think about this, let's use a value of 30. I'm coming in here, 30 divided by 16 integer is 1. Okay, so now I'm going to take 30 minus 16, which is 14. So 14 is the value I'm going to move on to the next bit. So I'm going to come down here, and now I'm going to divide that by 8. 14 divided by 8 is greater than 1, so int of that value is 1, so we're equal to 1. Now I'm going to take 14 minus 8 is 6, and I'm going to pass it down to the next bit. And I'm going to take 6 divided by 4, which is, again, greater than 1, so integer of 6 divided by 4 is 1. We come down here, and we're going to say 6 minus 4 is now 2. Divide by 2, that's 1, value 0. So now we drop off, so we have 16 is true, 8 is true, 4 is true, 2 is true, and 1 is going to be false. Then what we're going to do is we're going to write this bit out, again, as an array. We're just going to populate an array from 0 to 4 again, because we're doing because we're doing our bits 0, 1, 2, 3, 4, left to right. And now I'm just going to do a simple loop of GPIO pin 0, write the value of 0. GPIO pin 1, write the value of GPIO of pin 1. And then once it's all written out, or I'm sorry, it's going to do a 1-second pause between writing. It's going to write the value out. It's going to wait a second. Then it's going to come back up through the loop, continue onward until all of the values have been written out. So if I specify a value of 30, it's going to loop through this 30 times, 1, 2, 3, 4, all the way up to 30, representing the binary value of that number. And so let's just do that. Let's run it through 30. And we'll be able to kind of see now what the code is doing, if I can get up here. So it's going to go through, do our startup sequence again, and let's do 30. And now it's going to count. Remember, the first time through the loop, it's going to be a value of 1. So 1 divided by 16 is 0, we move on. 1 divided by 8 is 0, we move on. 1 divided by 4 is 0, we move on. 1 divided by 2 is 0, we move on. What's left? 1. 1, so we write a 1. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and so on and so on. So you get the idea. So we're just going through that loop. Now we're going to go through that loop 30 times. We're going to take the value, work our way down from bit 4 to bit 0, writing out the value as an array. And once it's done, we come back to ask for input again. I'm going to queue to quit out. And that is my solution to lesson 5 of TopTechBoy's Raspberry Pi class. I know this video got a little long, but I hope you understand the concepts and some of the ideas I went through, particularly the decimal to binary conversion idea that I had. So I'm Brian from Simply Brian Enterprises. Thanks for watching.